Alright, so here we have a graph comparing age and height. As many of you have already pointed out, the data is completely made up and done to serve a purpose. And the purpose that I wanted out of age versus height is it was something that you could grasp and get your head around. So we have a series of dots. What do you think those dots represent?
Every age.
Yep, so the height of someone over various ages. Again, not very realistic. If someone pulled their ruler out before and saw that an 11 centimetre baby, it'd be something like this big. I didn't say we were dealing with humans, okay? That was an assumption you made, not me. So we've got our mystery animal with our very conveniently linear looking, sort of looking heights over time. Now, with our creature here, we can see that the data, does that look very linear?
Yes.
I would describe the dots as not overly linear. I'd probably describe that as a cubic function, but for all intents and purposes, I'm going to approximate that it is linear. Happy with that? So what do we call that blue line? Line of best fit. Very good. So we got that far last time. What we struggled with was on the right side of the board. So we've identified that we've got a linear relationship first of all, and we know that linear relationships take the form of y equals mx plus c. Are we good with that? Yeah. Have we seen that before?
Yes.
Where m is our and c is our y-intercept. Happy with that? So y in this graph is height and x is. So what we're saying here is that the height of our creature depends on the age of our creature. Is that the case? Yes. Very good. So if I sub those values in, I'm just going to give height the symbol H and age the symbol A. If I sub those values in, I get the equation H equals MA plus C. Are we all good?
Yes.
Now, my C value is?
0.
And my M I need to calculate. How do I calculate my M? Rise over run. Do I take the rise over run of my points or do I take the rise over run of my graph? My line of best fit. That's the purpose of the line of best fit, to approximate my data. So I'm going to pick 2 points. I'm going to pick this point here and this point here. Does it matter which points I pick on my line? Providing they're on my line, it's all good. So my run is what? What's my run? 8 years. And what's my rise? Let's just go about 55 because again we're the pinnacle of accuracy here. Actually, I'm going to go 60 because it's a nicer number. Is it? No, it's not much nicer.
64.
56.
I'm going to go, that's 56 on the dot, okay? So 56 centimetres in 8 years. So my gradient is 7 centimetres per. So what's that tell me? Every year my creature's going to grow 7 centimetres, and I probably should have brought that over here. Okay, now, awesome, we understand that because we understand that things grow with time and that height is dependent upon age. I'm going to do something really crazy over here. Ready? It's going to be really hard. See if we can get our head around it. Where's my eraser? Over there. That's what I need. I'm going to change the terms age and height. Okay, so height's going to change here. I'm going to leave all the numbers exactly the same. No, I want that to be current, not volt, sorry. I want to make this current. What's my unit for current? What's this thing going to be? Can I write volts? No, probably not. All right. So I've got volts versus current. Now just get ready for this, right? I'm going to come back over to this side. Has anything changed on the right panel? Is it still a linear relationship?
Yes.
Is it still height?
No.
Now it is,
False.
which I represent with V. Age is now? I'll represent that with I. Still happens to be in amps. So, the only thing that changes now is that I've got voltage equals M times I. Does that look a little bit like an equation we've seen before?
Yes.
What's the M?
Gradient. Resistance.
So what have I found out when I've calculated my gradient? Now, when I was dealing with age before, does that mean that every year my specimen's going to grow 7 years? Did it grow 7 years every 7 centimetres every year, sorry?
No.
What was that? An average. So, what have I found?
The best fit.
With my resistance of 7 ohms, what have I found? Average resistance. Are we clear?
Yes.
Is that a lot easier than calculating the resistance at every point in time?
Yes.
That's why we do that. Now, what made the other day's work significantly more difficult is that we swapped voltage and current. Why would I swap voltage and current round? Make it difficult? Okay.
Volts go up slower than current.
Volts were a constant. Volts were a...
What's our x-axis in a science report? Independent variable. Where we were controlling the volts, correct? We were turning the dial, controlling how much voltage was going through our circuit, and we were measuring the current. Are we clear? So the reason it was a lot simpler was because the rearrangement of Ohm's law suits that situation. But is the mathematics any more complicated?
No.
No, it's just that instead of our resistance being M, our resistance will be what?
Oh.
No.
7 ohms.
If I swap the axes, what will my resistance be?
C.
V.
A.
So at least how many letters? Yeah, well, maybe we can
M
guess.
over 1.
1 over M. So the only thing that changed, instead of my gradient would go from being 7 to being 1 on 7. That was the only thing that changed. We're familiar with 80% of this process. We're familiar with how to get a line of best fit. We are familiar with how to create a linear equation or a linear relationship. We're familiar with independent and dependent variables. We know how to calculate gradients. The only thing we're struggling to do is then to link that to a known equation. Clear?
Yep.
And the way that we do that is think about what equation we have. Think about what the gradient represents in that equation. And if we go about it like that, it will take a bit of practice, but it should get easier. That's all well and good for a linear relationship. Do all of our relationships fall into the linear pattern? No. So we're going to start with linear and then work our way through to inverses, exponentials, that sort of stuff. Okay? But linear is a good point to start.